Resistance is defined as the opposition to current flow. The formula for resistance is equal to V divided by I. So R is equal to V over I, but more conventionally, it's written down as V equals I times R. As for objects, you either have insulators or conductors. If it's a perfect insulator, then it should have infinite resistance, meaning that it does not allow electricity to flow through. It's effectively as if a wire was cut. On the other hand, there are certain substances that have zero resistance, so no opposition to current flow, and those are superconductors. The next video, I'll let you watch that afterwards, and that has to do with superconductors. As for resistors, they can be connected in two different ways. If the left hand is holding the right hand, and they keep on doing that, then you have a circuit that's connected together in series. It creates one big loop. On the other hand, if you're trying to create a dancing train, then everybody's left hand are held together, and everyone's right hand are held together, creating a really long sequence, and that's known as a parallel circuit. These two circuits, they have their own corresponding advantages and disadvantages. For one thing, with regards to, like, let's say Christmas lights, each of those tiny little bulbs cannot handle the 120 volts coming from your mains. That voltage is too high and it'll cause the bulbs to burn out. So instead they want to share that voltage, and that's why with regards to tiny little lights, they're connected together in series. So each one takes a small portion of the big pie. On the other hand, with regards to your power bar that you plug things in, well, you want to be able to readily plug things in and unplug them when you don't need it anymore. In that case over there, you're just connecting to the two rails of the mains. And in that case over there, you're just plugging everything in parallel. So every device that's plugged into your power bar gets 120 volts. It's not shared. As for the advantages and disadvantages of each one, well, for the one on the left, as I mentioned, you can share the voltage so that they can handle the 120 volts, not entirely as one object, but shared amongst all of them. However, if one of the bulbs burns out, now you formed an open circuit. And with that open circuit, there's no more path for electrons to flow through, so that will be its disadvantage. On the other hand, with the loads connected in parallel, you can plug in anything anytime you want. And yes, they do have light bulbs built that way, classically in the 1980s. So if one bulb burns out, the rest of the light set still works. As for how you'd hook up a multimeter to the circuit, it is completely different between the two pictures. As for the picture down below, as for voltage, you'll want to connect your voltmeter in parallel with the circuit. So if I'm trying to measure the voltage rating of this circuit over here, here's my little scale device, the little arrow. With the two leads over here, the darker lead usually connects to the negative, and the red lead connects to the positive, and that way you can measure the voltage drop across the source. As for the loads, you'd rinse and repeat. So here is another meter. The meter usually has two wires, and the red wire usually connects to the side closest to the positive, and the darker wire will connect to the side closest to the negative. I'll rinse and repeat right over here as well. So the positive lead connects here, and the negative lead connects all the way down here. As for the diagram on the right, you'll notice that your outcome of whether you hook it up from here to here, or if you hook it up from here to down over here, the outcome is exactly the same. And that's due to the fact that you haven't gone through any load yet in the circuit. It isn't until you pass through a load in the circuit will the voltage drop. So for example, in the diagram on the left, if I was just to give you an arbitrary number, let's say that the initial voltage here that was measured by the source was 5 volts. Even if I place the red conductor all the way right over here, I will still register 5 volts as there is no voltage drop yet. It hasn't gone through a load. On the other hand, as there is a load right over here, there will be a drop. What will that number be? Well, it really depends upon the property of that load. But let's say hypothetically the drop here was a drop of 2 volts, let's say. Energy cannot be created or destroyed. So if you start off with 5 and you lose through 2 of them, how much remain? Good, 3. And if you were to read the meter reading over here, you would see 3 volts. When it hits all the way down here, it's lost all its energy. It'll just race back and get rejuvenated by the battery again. On the other hand, with the diagram on the right-hand side, if you start off with 5 volts here, as you pass through the circuit, you haven't gone through any load yet. So even at this point over here, you still register 5 volts. And if you place another meter right over here, you connect the red closest to the positive and the darker one closest to the negative, even this last voltmeter will measure 5 volts, as you haven't gone through a resistor yet. All right, it's still going through the same dark lead. It hasn't gone through any resistor, meaning that if I unplug this guy over here, it wouldn't notice a difference. It would still register the same result. Current, on the other hand, you have to play it differently. Current is trying to measure how many electrons flow per second. So if I want to count how many students enter into a classroom or into a gymnasium, where must I stand? Exactly. I must stand at the gates. And as I stand at the gate, I can then measure through how many are moving per second. So with regards to an ammeter, you need to take the circuit and you need to break an opening for it. Inside the opening, that's where you connect the meter. Once again, the side closest to the positive, you'll connect in red, and the side close to the negative, you'll connect in blue. And then this meter over here will tell you how many coulombs of electrons are flowing per given second. So, for example, let's just say that there was, I'll just use the number 3. 3 amperes of current that's measured here. All right, so 3 times 6.24 times 10 to the 18 electrons. It's a lot of electrons that are flowing per given second. Well, we can't just have electrons disappear in a circuit. So if I was to break open another opening somewhere else in the circuit, let's say right over down here, and then I reconnect it together with an ammeter, again, the side, oh, wrong way. The side closest to the positive, you'll want to hook up the red to it, and the side closest to negative, you'll hook up right over here. And if you're wondering, does it really matter the way how I hook it up? Well, if you hook up the wrong way with modern ammeters, it'll just show you a minus sign. In other words, the current's flowing opposite of what was intended. But with older electrical devices, especially those with meters, you might cause the needle to slam against one end of the screen, causing it to become miscalibrated, or yeah, miscalibrated, and you don't want that to happen. So in this case over here, if I had 3 groupings of electrons moving per second, well, they're not going to disappear. Even right over here, I'll still have 3 groupings move per second, as it's still through the same electrical path. 3 over here. So in this ammeter here, it will register 3 amperes of current flowing and returning back to the cell. Compare that with the example here. I'll use 3 as my arbitrary number. So let's say that we measure 3 amperes of current flowing through here. Well, we have a branch in the circuit here, so the current has to flow through 2 separate paths. Could they split off to 1.5 coulombs each branch? That possibility can exist. But if these two are not the same exact load and they're completely different, like for example, one is a TV and the other one is something smaller like a radio, well, the TV will consume more current. So you'll have one circuit path which will consume more coulombs per second, and on the other one, it'll consume less coulombs per second. So let's say hypothetically, in this first ammeter, it registers 3 coulombs per second. Through this one over here, let's say that because it demands more electricity, it measures a value of 2 amperes. Well then, logically, how many amperes of current flow through here? Excellent. 1 ampere of current. And you can see that they will rejoin again. The 1 ampere will rejoin with the 2 ampere, giving you a total of, excellent, 3 amperes again. You can't have electrons disappear in a circuit. So if you start off with 3, they may split off into 2 separate branches of the circuit, but when they return back, you should still expect to see 3 amperes of current per second. With that knowledge, there's actually rules that describe it. So there's a name for each of those rules. For example, what we just covered is known as Kirchhoff's current law. The quantity of current entering into a particular branch in the circuit, also known as a node, will equal the quantity that exit from that node. So let's say that we have 6 coulombs moving in to that node. The moment they pass through that node, in total it should still add up to, excellent, 6 of them. They don't have to evenly distribute out. It just has to add up to the same quantity that enter in. So if you call this original branch IA, current branch A, and you call this current branch B, and you call this current branch C, what can you generalize between these three? Excellent. IA is equal to IB times IC. Beautiful. That is the definition of Kirchhoff's current law. Kirchhoff also had another law, which is called Kirchhoff's voltage law, which states that if you place your finger anywhere in a loop in the circuit, if you go all the way around it, you'll net to a value of 0. Let's go through an example to clarify that. Let's say that we had a charge right over here. I can't exactly call it an electron because, as you know, electrons flow from negative to positive, so we'll just call it a charge. And the charge is completely depleted. It can be rejuvenated again by the source. So now to scale it as if it had a lot of energy, I'm just going to make it a lot larger. So now we have this charge with lots of energy in it. It has a high quantity of joule per that coulomb. As it flows through the circuit, it's not going to lose any energy until it goes through the first load. So it's going to lose some of it through the first load. It still has some left, so it's going to deplete the rest of it through the second load. And it's going to be like a ghost from Pac-Man and quickly race back to be rejuvenated again. And this process will happen over and over and over again in an electrical circuit. If I give numbers and context to this, let's say that the source over here had a voltage of 10 volts. And as this packet of energy passes through here, let's say hypothetically it lost 4 volts of energy per coulomb. Well, how much remains for this last guy over here? That's correct, 6 volts. And that's Kirchhoff's voltage law. So you can imagine it this way as well. I start off over here. Let's say the value's at 0. I increase over here. Now I am at plus 10 volts. I go through this resistor, and because it drops, I lose 4 volts. Well, over here, as we argued, if you lose 6 volts over here, then 10 minus 4 minus 6 will give you, excellent, 0. That is Kirchhoff's voltage law. And no, we don't have to start from over here. We could have theoretically started from up here, and I'll just do it in a different color. We could have started our experiment from up here. Okay, that's our reference value. Well, that's going to be equal to a drop of 6 volts, a gain of 10 volts, and another loss of 4 volts. And that will still net to a value of, excellent, 0. Same thing is also true if that's the same as this guy here. How about I go over here? Same as this red point over here. I start from there. I first lose 4 volts. Then I lose another 6 volts. And the battery rejuvenates and gives energy. That's why it's known as an electromotive force, because it gives energy to the electrons or to the charge to start moving again. And you'll notice that this also nets to a value of 0 volts. So this is the proper definition of Kirchhoff's voltage law. But in high school textbooks, they tend to skip out on that, and what they do is they make it nice and clean and tidy like this, which is perfectly fine. We're just moving the resistors over to the other side, and therefore the voltage drop across the source of 10 volts is equal to the sum of the voltage drops of 4 and 6 volts. You'll still arrive to the same exact answer. Choice is up to you which way you decide to describe it. But I'll just tell you this, that in university, often we describe it this way, because this can be used for any problem. Once again, just emphasizing that we're talking about current flow. We're still going by the conventional current, because this person over here said it wrong, and we've just been doing it wrong ever since. About 300 years now. Let's try out this example here. Pause the video if you want to screen capture this first so you can work along with me. This is kind of like the game of Sudoku. As you may know in Sudoku, as long as the numbers 1 through 10 go across this way, 1 through 9 are visible across, 1 through 9 are visible vertically, and within its own little, not quadrant, but 9 or nonagon, if you want to call it that, the numbers 1 through 9 show up there as well, then you've played the game correctly. As for this guy over here, the rules are slightly different. As for this one, here are the rules. V has to equal I times R. P has to equal I times V. With regards to Kirchhoff's law, any sort of loop must net to a value of 0. And with Kirchhoff's current law, any current going in must be equal to any current exiting out. So you need to abide by all those rules. All right, rules numbers 1, 2, I suppose 3 and 4 that we described about, as well as these additional rules that were briefly mentioned earlier, where if you have one loop, as no electrons are lost or gained, then the current through every single item will be exactly the same. On the other hand, if you have a circuit connected in parallel, the current will then be distributed through all the loads. So we have to abide by all 6 of these rules to ensure that this game will be played properly. In fact, there's a 7th rule, and I'll explain that 7th rule afterwards. So as long as all of them are true, you've played the game just fine. You could technically start anywhere, but as I have a tiny little number 1 somewhere here, oh, where did it go? I don't know. Cheat. Okay, number 2. I guess that's my first number. We'll start by proving this point over here. What should the answer be? So that's through R1. What is the current going through here? Well, through the source, we know that there is 0.846 amperes entering in. And if you're wondering about this minus sign over here, there are some textbooks that ignore the minus sign, and that's perfectly fine. The only reason why there's a minus sign there is because of what exactly this thing is. This is an EMF, an electromotive force. If we remove the battery from the circuit, would the electrons want to move naturally? No, they'll just stand still and do nothing. If you want them to do useful work, you need somebody to push it or to force it, and it needs to be electromotive to force the electrons to flow. And now you know. So to state that the electrons are moving against their will, that's why there's a minus sign here in some science textbooks. Okay, but as I said, if you want to ignore it, that's fine with me. So 846 milliamperes of current is flowing into this node here. Some of it will go through I1, and the rest of it will go through this branch over here, I2. And we can see that we have a current flow here of 0.308 amperes. So if you have 846 going in and 308 coming out, how much goes through I1? Well, it's just the difference of those two numbers there. Of 846 milliamperes, subtract 308 milliamperes, giving you 538 milliamperes flowing through the circuit here. Awesome. Now let's try to answer this part over here. And yes, there's 2 ways of answering it. You could first off, by knowing that V is equal to IR, where is it? V equals IR, you can multiply these 2 together to get to the answer here. That's one way of doing it. But how about I show you a harder way of getting to that answer? All right, because as I said, all these rules need to work out for it to be valid. So here's another way of approaching it. R1 has a measurable potential difference, but that could be figured out by this loop over here. Vs is a gain of 10 volts. R1 will lose a certain amount. We don't know. Through R3, we're going to lose another amount, and we have the value of R3 of 4.62 volts. So 10 minus 4.62 gives you what? 5.38 volts, right up there. And once again, if you decide to do it this way, V equals I times R, as you have those values, well, this just simply means about 50% of 10, which is around 5-ish. There you go. All right, so there's multiple ways of proving that. Next box. Let's prove this blank right over here. How can we solve it? R5. We have the resistance and we have the voltage. These are the two values that we have, and you need to have at least two knowns in order to solve the rest. So as we have the voltage, we don't have the resistance yet, but we know that if we sub this, if we arrange this for I, because we don't have current yet, I is equal to V over R. We could sub that right into here. So P is equal to V over R times V. So P is equal to V squared over R. Pull out our calculator. And I guess I'll just give away the answer here as my calculator's not showing up. All right, so you take 3.85, you square it, around 10-ish, divide by 10, will give you around 1-ish. There you go. One last thing to emphasize for you is right over here. If you multiply a negative by a positive, your answer is going to be a excellent negative. So let me just clarify this minus sign now. Once again, if you decide not to show that on any quiz test or exam in high school, it's perfectly fine. It's not normally stated that way. But often in science, we want to give conventions for plus and minus, where positive means that it's a load and negative means that it's giving away energy. In other words, it's a source. And that has to be the case over here. It is a voltage source, so it is losing 8.46 watts. And here's where I'm going to play out or share with you the last rule. As this is a closed system or an isolated system, you want to think about it that way, the total energy that's being emitted by this source over here has to be equal to the total energy absorbed by each of these loads. And because this energy is moving as time goes by, we don't call it energy, we call it power. So in other words, the total power exiting from the source has to be equal to the total power absorbed by each of the loads. Meaning that this line over here, if you add it up, it has to net to a value of, excellent, 0. And that's the last piece of the puzzle. Now, in some of these electronic Sudoku problems, maybe you need to use this as one of your starting moves, that this row over here will net to a value of 0. Or you may want to use that as your last gameplay to make sure that everything's correct. It's a good way to check your answers, because that entire row must net to 0. If it doesn't, you know you made a mathematical mistake somewhere. Anyways, I think I'm going to leave you with that. Yeah, have fun with your homework, and I'll catch you in the next episode. Or maybe we'll continue with this. Yeah, let's take up the homework now if you're struggling with it. All right, so in this case over here, if it helps, you by all means just populate away so that you know what exists here. You know that this is 100 volts, and you know that this is 75 volts. In fact, with that, I can already see the solution to our first problem. Here is our loop. It must net to a value of 0. So you gained 100 through the battery. You must lose a quantity through here and 75 through here to net to a value of 0. You know that it works out to 25. So R2 must be 25 volts. Also, if you recall, if it's connected together in parallel, it'll share the same exact voltage. So if this was 100 volts and these are parallel to each other, then R1 is also 100 volts. You'll see that R3 and R4 are parallel to each other, so they must also share the same exact voltage. And as long as you have two givens, you should be able to solve for the rest either using P equals IV or V equals IR, or maybe a hybrid version of those two subbed into each other, which is P is equal to I squared R, or P is equal to V squared divided by R. Again, it's just the substitution of this into the previous equation to create these secondary equations. I'll go through some examples randomly with you. For example, if I want to figure out the resistance over here, well, resistance is equal to voltage divided by current. So, handy dandy calculator, a voltage of 100 volts divided by 5 milliamperes, or 0.005 amperes, will give you a resistance of 20 kiloohms. You can rinse and repeat for this one here as well. So 25 divided by 0.005 gives you 5.0 kiloohms. 75 divided by 0.075 would give you 1 kilo ohm, and the last one is 75 divided by 0.004, which gives you 18.75 kilo ohms. That's a very weird number. Oh well, that's what I chose. As for power, power is equal to voltage times current. So 100 volts divided by 0.005 amperes will give you 0.5 watts. And I hope you get the idea for the rest of it. That's all you're doing for the remainder. I just want to show you something neat before I move on. How about I do the next one, which is 25 times 0.005 gives you 0.125 watts. As for this last column over here, you could either multiply these two down to get to your answer. 5 times 4 is 20, 4, 7, 28, so it's going to be, I guess, 0.3 watts. That's my guess, 0.3 watts. But there's another way to check that out, which is -1 plus 0.5 plus 0.125 plus 0.075 is equal to 0.3. There you go. As I said, there's multiple ways towards filling this in. Choose whatever way you want to start off with first, and just be consistent with that, and you'll get to your final answer. In fact, I'm just looking at another way of solving the same problem one more time before we move on. If we know that R1 is 5 milliamperes and R2 is also 5 milliamperes, that means that over here it must have been 10 milliamperes. And you can try it out even by doing P divided by V, and you should still arrive to the same answer. Yeah. All right. Oh, before I move on, I totally forgot about this. If you have troubles trying to see the picture like this, some people like to see it in a waterfall setup. In other words, this gains all the energy, and from there, everything trickles downwards from there. So here's my buildup, and from here, it's going to trickle downwards. First, the waterfall is going to fall through R1 and fall all the way down to the basin to be rejuvenated and pumped back up by the battery again. R2 is going to lose some of the energy, but then at this plateau, there's going to be two smaller waterfalls on the side. And that's why we have a picture that looks like this. So this is another way just to see how things work out. So if you know that Vs is equal to 100 volts, then R1 is equal to 100 volts. If R3 and R4 are both 75 volts, then R2 had to be 25, because you started off at 100, you lose 25, so you end up with 75, you lose 75, and you're back to ground zero to be recharged again. And current flow can also be described this way as well. So you know that the math has to work out logically. When it comes to test time, do you need to redraw it in a waterfall now setup? That's up to you. If it helps you visualize it, by all means. But you could easily interpret everything just by taking a look at it in the standard schematic format, where you usually read it from left to right. So you have your source on the left and all your loads on the right-hand side. This example over here, if you fast forward over here because you're finding this a challenge, and that's because we have two cells connected, and that makes things a bit more difficult. But it shouldn't change any of our rules. For example, the first rule I'd probably go with here is the big circle here. This must net to a voltage of, excellent, 0. So whatever you gain over here, you're going to lose over R4. So do we have VA and VB? We have VA, and VB is not too hard to calculate out right now, because VB is equal to negative 12.5 divided by negative 2.5, which will give you positive 5.0 volts. So you're going to gain 5 volts here. You're going to gain 7.5 volts here. So 5 plus 7.5 gives you 12.5 volts. Maybe you want to see this in a waterfall setup, and that's fine. You'll see the VB is all the way down here. Okay, so if we started off assuming that this is 0 volts over here, not that you had to, but let's say that was 0 volts over here, you gain 5, you gain 7.5, and then you drop in your R4. What's next? Well, we could fill in these two values quite simply. I'll just write down the formula here. You'd use P is equal to IV for this one over here, and R is equal to V over I for the solution over here. Same as the P over here, P is equal to I times V. Okay, so as for the current over here through R1, I'm sure there's two ways of solving it, because we know that R1 is equal to just redistribution through R2 and R3. So if we add these two together, we should arrive to the answer here, which that should work out to 2 amperes. Another way is P is equal to, or sorry, I is equal to P divided by V. So 10 divided by 5 also gives you 2 amperes. In fact, there's a third way to solve this as well. Oh no, there isn't. Sorry, I was thinking of power. Two amperes. Resistance, there's many ways to solve it. So how are we going to solve for the rest of this? I think I'm going to have to solve for the voltage here. R2. Well, we can draw a loop over here. If VB is equal to 5.0 volts, and R2, we don't know yet, but R3, we don't know yet. This is a good question. I'm going to pause the video. You can't solve this loop over here yet, and that's because we don't know R2 and we don't know R3. So I'm going to avoid this loop, and I need to look at one where there is some viability. I do have the value for R1 and R4. That's one way of solving it. In fact, yeah, let's try it this. No, that's too hard. We'll do it this way. This one over here. And the reason why I say this one's too hard is because when do you know when to add and when to subtract? And if this is a waterfall, then you know that if you go against the waterfall, then you should start adding as opposed to subtracting. Okay, so yeah, let's just avoid that. Let's just go through this loop over here. So we have a gain of 7.5 volts, and R1 we lose 5 volts, meaning that through R2 it should have a value of 2.5 volts. So that when we go through this last loop over here, we start off at 5, we subtract 2.5, and that means that R3 must also be 2.5 volts as well. Well, P is equal to I times V, P is equal to I times V, and R will be equal to whatever formula you want to do. For example, V divided by I, R is equal to P over V squared. V squared divided by P. All right, so there's many different ways of answering that last one there. All right. Third example. What do I know so far? Well, I see that R3 and R4 are parallel to each other, so R3 and R4 should share the same voltage. That'll be my first step. What else do I know? I know current, because current through the source is at 150 milliamperes, so through R1 it should also be at 150 milliamperes. If you're wondering which way is the right way of writing it down, they're both correct, so the preference is up to you. So if you have 150 going through here, and R2 has 50 of it going down here, that means that between R3 and R4, that must equal to a total of 100 milliamperes. How many is going through each one? Well, that we don't know yet, but we know that when we get through here, this would be 100 milliamperes as well. So R5 is 100 milliamperes. And the math should work out because 100 plus 50 should equal to the quantity returning back. Once again, with regards to Kirchhoff's current law, you can't have electrons disappearing. So whatever you start off with, you should have that many returning back. It's a good way to check it out, or to check your answers. Okay, what else can we solve right now? Oh, right over here. We could solve for I here. I in this case over here is equal to V divided by R. So 2 volts divided by 25 will give you 80 milliamperes. And we did mention something over here. These two must equal up to 100 milliamperes. So if one of them is 80, the other one must be 20 milliamperes, because 20 plus 80 in their branches sum up again to 100. With that said and done, I think the rest should be fairly straightforward now. For example, P is equal to IV, R is equal to V over I. So P is equal to IV, R is equal to V divided by I. As for the voltage here, maybe we want to know that right now. Voltage is equal to power divided by current. So 0.3 divided by 0.1 will give us 3 volts. That looks good. And then the resistance can be equal to whatever formula you want to use. That's fine. With that 3 volts, that helps us out with the next part. Because if I want to draw this as a waterfall analogy, here it is right over here, we just stated that R1 has a voltage of 3.0 volts. R3 and R4 both share the same voltage of 2 volts. And R5 is 3.0 volts. Well, everything up to here, 2 plus 3 gives us 5.0 volts over here. So R2 must be at 5.0 volts. Lastly, when we go through the entire loop from top down, we know it's equal to 3 volts plus 5 volts, which gives you 8 volts. With that, I think the rest of it's manageable, because yet again, P is equal to I times V, and R is equal to V divided by I to fill in the rest of the table. One last thing to always do, just to check your work, is to add up all of that, because that should equal to a value of 0 watts. All right, when you add all of that together. Excellent check. For more fun adventures like this, I guess go through the review package. I think there's another review question at the end. Have fun.